derivatives of exponential functions. I'm not going to really prove the formula for it. All I'm going to show you, if we have exponential function with base e like this, the question is, what is y prime? What's the derivative for this? Okay, so if we write it y equals e to the x or f of x, the same thing, then y prime, the derivative of this, or f prime, is really itself. Nothing changes. Nothing changes. So this is the same as y prime or dy dx. That's called first derivative. And to apply this, we can ask you to find dy dx for each of the following. Y equals 5e to the x, or y equals x cubed e to the x. Y equals x squared over e to the x. So how do we find the first one? The first one shouldn't be that difficult. All we have to do is the constant, you can just leave it as is and find the derivative of this function, which is ex. So the derivative of 5ex is 5ex. What about the next one? I see two functions, x cubed times e to the x. So do I find the derivative for the first times the derivative of the second, or what do you think we should do? We should use what?
Product rule.
Good job, product rule. So the product rule said you find the derivative of the first one times the second one plus the first one times the derivative of the second one. So from here to here, we use product rule. Product rule. But it's not done yet. All I did, I just set it up. I only set it up. So to finish with this, the derivative of x cubed is what? 3x squared. And ex stays the same. X cubed. What's the derivative of ex? Is ex. Okay, so I'm gonna recall here on the side, just so you remember if you forgot, the product rule says if you have u times v, then y prime is u prime v plus uv prime. That's called product rule. And for the next one, the quotient rule, if you have u over v, y prime is vu prime minus v prime u over v squared. That's called quotient rule. Quotient rule. So now I recommend you try number 3 on your own. See which rule you have to use, product rule, quotient rule, or none of them. So for number 3, we're going to be using the quotient rule. Y prime, the denominator times the derivative of the top minus derivative of the bottom times the top over the bottom one square. So y prime equals 2x e to the x minus x squared e to the x over e to the x squared, like e to the x times e to the x. And one thing we are supposed to do here is to simplify. Factor e to the x out. That'll leave 2x minus x squared. These cancel, so you get 2x minus x squared over e to the x. The question that people ask, what happens if it's not like just e to the x? How about if y equals e to some function like f of x, not x, maybe x squared, maybe 2x, maybe something else, then what would be y prime in this case? Y prime would be the derivative of that exponent times e to the f of x. e to the f of x. So if I apply it just to the one we started with, e to the x, so watch what's going to happen. It's going to be the derivative of x times itself. Well, what's the derivative of x? It's 1 times itself. And that's why we got e to the x. So the derivative of e to the x is e to the x. How about if something different, like e to the x squared? Or y equals e to the negative x squared plus 5x minus 1, something like this. What would we do in this case? Well, again, y prime is going to be the derivative of the top times itself. So y prime is 2x itself. Okay, what about the next one? Y prime is the derivative of the top times itself. Okay, the derivative of this is negative 2x plus 5 minus 0 times the function itself. Another example, y equals 3t minus 5 e to the negative 3t. Find y prime. So y prime is, there's two functions. We have to use the product rule. We take the first one derivative times the second one plus the first one times the derivative of the second one. Y prime equals, what's the derivative of this? 3 minus 0, and this stays the same. This stays the same. Derivative of this one is the derivative of the top based on the formula I just gave you, negative 3 times itself. And you can factor out the 3 and e to the negative 3t. And what is left? 1. This one is gone out. There's a negative left. Negative 1 times this. Then what we do next is simplify the quantity inside the bracket. 1 minus 3t plus 5. 6 minus 3t. You can leave it like this. If you like to factor 3 out, that's fine too. We can ask a different question. Find d squared y dx squared. This is the second derivative. If y equals e to the 1 over x squared. So we have to differentiate this 2 times. 2 times. How do we differentiate this? First thing to do is rewrite it. Bring this up. Becomes x to the negative 2. So 1 over x squared, if you bring it up, becomes like this, right? It's much easier to work with this than working with fractions. Always avoid working with fractions. So I'm going to find the first derivative, y prime, which says the derivative of the top times itself. What's the derivative of the top? It's negative 2x to the negative 3 times this itself. Because you bring the negative 2 down, subtract 1 by the power rule. That's the first derivative. And you don't have, there's no reason to simplify until the end. Then we need to find the second derivative, y double prime, which is d squared y dx squared. How are we going to do this? This is by itself a function, and this by itself is a function. So we're going to find the derivative for the first one times the second one, plus the first one times the derivative of the second one. So the derivative for this one, you multiply negative 3 by 2 is 6, x to the negative 4, and keep this the same. Keep this the same. And now what's the derivative for this one? Is negative 2x to the negative 3 times itself. The first one stays as is. The next one is 4x to the negative 6, x to the negative 2. Wait, there's a negative sign here. We can factor out, among the 6 and the 4, we can factor 2. For the x's, we can factor either one of them. Usually we factor the smaller one, x to the negative 6. And among the last two, we can just factor that term. Now it's tricky what is left. 3 is left because 3 times 2 is 6. And here the x's, that should be x squared. Because if you multiply x squared by this, it should give you this. And this one is done down here, plus 4 and 2, it's a 2. That one is gone and gone, so that's what is left. But usually I tell my students, I don't like to see negative exponents in the answer, so keep this one here, and 3x squared plus 2 as is. Bring the x to the negative 6 down, and actually e stays up there. E to the 1 over x squared. Any questions about this? how do we apply derivatives in applications as we did in the previous section? So let's say Robert deposits the $20,000 that we started with in the previous section in a savings account that earns 4% annual interest, and this is compounded continuously as we did in the previous section, compounded continuously. The value of his account after T years is given by A of T equals 20,000 e to the 0.04 t. This formula came from the previous section. We want to find A at 10 and A prime at 10. A at 10, this means that's what would be the amount after 10 years. So A at 10 is all you have to do, substitute T10 is 0.04 and 10, and then put that into the calculator. That gives us 29836.49. So it's 29,000. So this means if you want to interpret this, you say after 10 years, the money will grow to this much money, $29,836.49. That's the meaning of it. And we rounded to 2 decimal places. The second part, we need to find the derivative for that and evaluate it at 10. So how do you find the derivative of this? A prime of t is 20,000. Bring the derivative of this is the derivative of the top, which is 0.04 times itself. Do you guys agree? It's the derivative of the exponent times the function itself. And then if I want to find A prime at 10, all I have to do, 20,000, 0.04, e to the 0.04 times 10, like that. You're going to put that into the calculator, as I'm doing right now. And that would give us 1193.46. Okay, now what does that mean? What's the meaning of this? To interpret this, this is saying after exactly 10 years here, in this case, 10 years, as you notice in the previous part of this problem, the value of Robert's money will be what? What was the amount? 29,836.49, right? And at that instant, the value is growing at the rate at the rate of that number we got, 1,193 and 46 cents per year. That's how you interpret it. One last example here to show you how to apply this even more. It's a word problem. I'm not going to write the whole thing down, but I'm going to say it. So the example says it's reasonable for a manufacturer to expect the daily output of a new worker to be low at first and then increase over time and then level off at some point. So a manufacturer of LED flashlights determines that after T days, so after T work days, the number of flashlights produced per day by the average worker can be modeled by the equation n of t equals 80 minus 60 e to the negative 0.12 t. Part A, find n for t equals 1, 5, 10, 20, and 30. So this should be a straightforward substitution, right? So you're going to need to find n of 1, n of 5, n of 10, n of 20, n of 30. So we have to substitute them in. So for the first one, 60e negative 0.1, 2 times 1. And for this one, 80 minus 60e negative 0.12 times 5. And we do the same thing for the rest of them. So let's calculate the first one. That gave me, this is about 26.8. We can do the same thing for this and get 47.1. For the next one, we do the same. We get 61.9. And the next one, it gave me 74.6. I'm rounding to one decimal place. And the last one gave me 78.4. So I can make a table of values here for t and n of t. It was 1, 5, 10, 20, and 30. We don't need this here. And the values I just obtained, I can summarize them within the table. So that was 26.8, 47.1, 61.9, 74.6, and 78.4. That's all they ask us to find here. For part B, graph n of t. How do we graph n of t? So we're going to graph it using the t, n of t, using the table I just created. So it goes up to 30. So maybe you can go by increments of 10. So 10, 20, 30. And then the highest value is 78, so maybe go up to 80. So the middle one is 40, middle is 20, 60. That's a 0 here. So the first one was 26 something, so maybe here. Next one 5, which is the middle here, 5, and it goes up to 40 something. Next one 10, 61. Next one 20, somewhere here, and the last one up there. So it's growing and is getting closer and closer to some number. It seems it's getting closer and closer to 80. So if you extend this line, the line is getting closer and closer to 80, or the graph. Do you guys see that?
Yes.
So find n prime of t and interpret this result as a rate of change. Assuming everyone done copying. Again, n of t was, just to rewrite again, 80 minus 60 e negative 0.12 t. We can find n prime of t. This is 0 minus 60. You need to bring that number down, the derivative of the top times itself. N prime of t equals 7.2 e to the negative 0.12 t. That's the derivative for that. And how to interpret this? This is saying after t days, because the problem was talking about work days, t days, the average worker is producing flashlights at a rate of the number, the thing that we got, 7.2 e to the negative 0.12 t flashlights per day. Note, based on the graph, above, we see that the worker output levels off at no more than 80 flashlights produced per day. So to summarize this section, we went over the derivative for e to the x. We went over the derivative of e to any function in general, and then applications to that. How we find the derivative using the product rule, the quotient rule, and then how we apply it to an actual example from real life situations, including the compounded continuously functions and an example from or about like workers and how many flashlights they can produce per day. They start like producing a little bit, and then later on, as they gain more experience, mathematically it shows us that they can produce more and more flashlights, and then it's maximized at, per this example, at 80 per day, no more than 80 per day.